All right, we're continuing on with our class 17, and we're going to talk about power screws and their purpose. And they're going to have, of course, we're transmitting torque, transmitting power by way of torque and turning it into a linear motion. So you could turn torque into force right here. You can imagine that as we turn the handle on a C-clamp, it crushes the thing on the inside. If it was a jack, when we turn it, we lift it up. We have two basic, most common threads that get used with power screws will be square threads and Acme, where there's a slight angle. For most of our work, we're just going to deal with the square threads because they're easier to take a look at. Here's from another book, Collins. It's showing you some things we want to know. One of our impediments to using power screws is going to be friction, and we'll see that that's sort of a common theme. We had friction in brakes that we had to be concerned about. Now we have a friction in power screws that we want to take a look at, because that's going to be some of the resistance to the torque is going to be based on friction. And it's not only going to be the friction between the threads and the nut, but it's also going to be friction between the collar or anything that's supporting right there, okay? And so some things will actually rotate. They're showing this as being bolted right here. So this thing actually might rotate friction against the side and friction against whatever it's pushing down. But now we have a bearing that we could have inside here, and that bearing, it looks like it's supporting it radially, but it could also support it axially as part of this. So you have to kind of like think in those terms that there's lots of different places where this could have friction. Like for instance, right here, there's going to be a friction right here in that surface. But this right here is a nut. They're not showing the internal threads as part of it, as this thing is moving up and down and lifting up this platform. So that's the idea. Now you could have, here's one where they were showing the single threads versus the double threads versus the triple threads. And as I mentioned in the last class, a water bottle top is an example of a triple thread, or a toothpaste cap. So don't want to go through this too far, but to figure out the torque that's required to raise and lower, we take a free body diagram of a wedge of a thread, right? So we kind of unwrap a single thread for an entire circumference right there. So that's pi times the mean diameter right here. So let's go back and define the mean diameter would be halfway between the outside diameter and the root diameter would be the dm. Of course, it extends to the other side down there. And note that the pitch is one thread length right here, and for square threads, the gap between them is p over 2, and the height is p over 2 of a single thread. Notably, that there probably would actually be a little bit of difference, and there needs to have some clearance in between the threads. So the thread width is probably going to be a little bit smaller, and the gap is going to be a little bit bigger. The same true would be on the nut, but you would have it just the right amount. So over on the left, we have the rate. This is the condition where we're going to raise a force, and what we see that there's a friction being applied right here. So that's the friction, the resistance of the thing. Here's the load that's being placed, and here is the force to raise this piece right here. The same thing over here, but we have the lower. All right, so we're going to have equations that we've developed from this that are lower. And by the way, be careful here in the figure. This is just saying it's in the x direction. It's not saying minus x. And they're using the lowercase l. Remember that l is equal to p if it's a single threaded thing, right? So L is the lead. It's going to be it would be 2 times P if it was a double threaded, and 3 times P if it was a triple thread. But we're mostly just going to deal with single threads. Lastly, we have this lambda right here, where lambda is this angle, and it's by definition L divided by pi over dm. Of course, it's in radians right here, so it would be the inverse tan if we were going to try to get it into degrees. So if we do a friction force balance, and I think I haven't left myself enough room right here. So, because I ask this question after I've written a bunch of stuff, I left space on your page, but not here on my screen. So I'm going to keep this, and I'm going to add in a blank slide so I can write this out. And I kind of need to turn my screen over while I'm here. So let me flip this over. Detach it and flip it. I do like the Surface. I guess it's called the Surface Book, not a Surface Notebook. I don't know, but anyway, let me see. Let me actually. Can I move this thing? Let me see. Move. Can I? I'll cut it and put it down here somewhere. Paste. Can I paste it? There you go. Paste it like a picture. There you go. Stop asking me for design ideas. I don't care about your ideas. And then all of this, let me raise this up. I mean, this was all configured for the projectors at school. So there you go. Okay. So for this force derivation here, let's change to purple. I like it better. We do the sum of the forces in the x direction. It's going to be equal to 0. So that's going to be, let's see, I guess, did I do the lower? I guess I only did the lower example. Yeah, okay, so here this is going to be for a lower. This is, of course, in the book so that you can read it yourself. But I put negative PL, right here, so you'll see negative PL minus n, all right, so that's going to be the total n, times the sine of lambda plus the coefficient of friction times n times the cosine of lambda is going to be equal to 0. And then the sum of the forces in the y direction equal to 0. And we take, that's going to be the load F plus n times, oops, in this case is the cosine of lambda, right? And plus F times n times the sine of lambda equals 0. So we're going to try to pick out all those things, and you could see, there you go, because lambda is right in there, and lambda is right in there. So yeah, that all works out. So if we substitute, if we combine n, right? So that's the thing that we want. We redistribute that n, and I think we also substitute this right here. So the combination of that, and you're going to find that the torque to lower, right? So torque in this case is going to be PL times, I think it's going to be dm over 2, right? So that force that we have, the force required to lower something is going to be put right into there. And we're going to put it back over and find what the torque to lower is going to be F dm over 2 pi F dm minus L divided by pi dm plus FL. And did I write down what this equation is? This is equation 8.2. If we do the same thing to raise it, we end up with the force dm over 2 times L plus pi coefficient of friction dm divided by pi dm minus coefficient of friction times the lead, which is actually the pitch, right? That's pretty much. And this is going to be equation 8.1. And I asked the question, when is this self-locking? Right, so that's the big question. When is it self-locking? It's going to be self-locking when the force is when this right here is a positive torque, right? If it's a negative torque, that means you need to apply a torque to keep it from spinning out of control. Can you picture that? Like if it was loose enough, if there wasn't enough friction, and you put like if we had like a big jack right here, right? And so here's our threads and a nut right here, and maybe this is the thing that's like the main ground thing that's holding apart. And like maybe we were able to turn a handle around this nut to be able to lift up a big weight. Can you imagine this weight being enough, or maybe the friction being low enough here, that this handle would just start spinning around on its own because of this condition? Well, that is possible, but it's only possible if this becomes negative. And the only way that it can become negative is if L right here is greater than pi f times dm. Therefore, pi f dm must be greater to the L for self-locking. Right? And by self-locking, that means that we don't have to apply a torque to it for this weight to just stay there once we've stopped trying to raise the thing. Now, we could also want to take a look at what power, the concept of power screw efficiency, which we should have placed up there. We take a look at which one? Okay, think about the torque that would be required to lift something if there was no friction. So if there was no friction, all of a sudden what we're left with is going to be TR is going to be F dm2 times L divided by pi dm right here. And we refer to that as a TO right here. So if there was zero amount of friction, I don't know what the O stands for. I think it might mean that friction is equal to 0. We end up finding that it's just going to be FL over 2 pi. And if we want the efficiency, they decided to go with lowercase e for efficiency. We would say the torque with no friction divided by the torque with friction right there. So the ratio of the torque without friction divided by the torque required to raise the thing. And if we were to have Acme threads, by the way, as an example, the torque required to lift the thing is now going to be L plus pi f dm, and then the secant, oops, I didn't finish my secant, the secant of that angle right here, and they're considering this to be 2 alpha right here, which I think they said was 29 degrees. So whatever the hell was that, 14.5 degrees would be what alpha was equal to. I left out some things. So it goes pi dm minus FL secant of alpha, and this just would be F dm over 2. So that's the torque to raise for Acme threads, and that's equation 8.5. But we'll just use square threads most of the time. Now, also, when we have to figure out the torque to raise, that is just due to the threads and due to the friction in the threads and the load. And there better be some friction on the threads. We actually relying on the friction of the threads. And I want to make sure that I remember to make an important point about this right now. But here in a second. So the collar friction is something similar. A simple equation, but now we have a separate coefficient of friction, and we have some imaginary diameter that they decide DC is going to be like this, kind of an average thing, but it's like the collar friction diameter is what we call it. So the collar also can have some friction. So we want to have when we look to find to raise it. We have the raising torque and the lowering torque, and we want to get the total torque. So the total torque to raise is the torque to raise plus the collar torque, and the same thing because it doesn't really, the torque due to the collar still makes it difficult to raise the thing. So this is the amount of torque that you need to apply to this screw to be able to get it to do its function. And just as a typical values, okay, so here's the important thing I wanted to mention. We are relying on the coefficient of friction to be able to calculate these things. And that's a very hard thing to actually find. If you want the coefficient of friction, take a look at table 8.5 for F. And what you'll find is that for like steel, that's typical, it's going to be 0.15 to 0.25 dry, and it's going to be 0.11 to 0.17 oiled, right? So actually, whether the thing has lubricant in it or not makes a decision about whether it has a coefficient of friction. So it's a little bit unsettled. We don't quite know. I mean, there could be corrosion in there. There could be some grit that could be inside there. They could have made some really, really, really smooth surfaces, and so now the coefficient of friction is less. So there's a degree of uncertainty that we have. If we wanted to have the collar coefficient of friction, that's going to be table 8.6 for F. I keep leaving out the R. FC, and that we have the typical ones are going to be 0.19 to 0.12 for running, and it's going to be 0.15 to 0.17 for starting. Right, so we know that we're going to have a static coefficient of friction. So to get the thing started, we're going to have a certain amount. It's interesting to me that they didn't really say the running and the starting for the threads onto the thing. So you can imagine. Now I want to do stresses in threads, but I'm going to make this a separate video. So I'm going to end this one right now, and so we could go back to, if you wanted to get more information, you'll be able to get these videos and watch them separately.